we still got our first motor here, and the big thing is it's got its little output pulleys right here. There. You can see the output pulleys with the strings attached. And as this motor turns, these strings will wind up. You can see, I mean, they're just gonna spin in place because they're not pulled taut, which is why they need guidance hoses. But that they will reel up on there like a fishing reel as this spins, and that will then pull on the muscle. Now the problem I ran into is this. That's not a geared down motor. This spins at like 3,000 or 4,000 RPM. And so with 16 turns of that, I actually measured it, it draws in 6 inches of that string. 6 inches from 16 turns. And so I did a whole bunch of math and a whole bunch of research, and here's what I found. Okay, so that's pretty much the motor you'll find inside a standard hobby servo. Alright, so when I say servo, a servo motor, what I'm talking about is the following. So this is what a servo motor looks like. This is what we were originally going to control our robot with, which is what most people use. The problem is, I sewed this onto my robot, and its output horn and its everything was just huge in every direction. I mean, you have to measure from here to here, and then from the top of this output horn to the bottom of this. Just one servo could not even fit anywhere near the wrist of a human wrist bone, because it was so thick and so long and so fat in every direction. It didn't have a slim profile, so I couldn't put it inside here on the robot because it would be sticking out. And so I could only put these where large muscles were in the forearm, so I had to put it like right in the beefiest part of the arm. But even then I could only fit like 2 before the third one's sticking out. Well, I'm like, okay, you're telling me I can only fit 2 motors in the entire forearm? That's a big problem. And that's because the form factor of these is poor. And so I decided, you know what? I'll just take the motor out and go with that and create some kind of pulley system. So I had this idea of some kind of pulley system, and then I've been working on that concept for a while. But let's go back to what I was saying. So here's what the outside looks like. Here's what's inside. Here's what's causing all the problems. Okay, so there's its gear train, it's called. This is its output horn. This is the motor right here, and that's the type of motors we're using for the robot. But I'm pulling all the rest of this fluff out and just having the motor. Now I can fit a lot of these motors, which you can see here, I believe. Nope. Well, actually, this is kind of interesting, though, that I pulled this up. I'll show you guys real quick what this is all about. Okay, so here's one of those very same motors we just saw from right here. This is the same motor. Okay. And you guys saw the little pulleys I put on the end. These little plastic pulleys. Okay. This is going to be a guide system, which I modeled, where the strings coming off the pulleys go through these holes. You can see the holes there. And then they go into these guidance tubes. And then these guidance tubes can take the string and go in any direction we want. So they're going to go up and then against the robot's bone and then travel up to here. Okay, so that's what the guidance tubes look like. And this initial one is just to guide the strings perfectly onto their wrapping onto this output shaft with the little plastic pulleys that are also 3D printed. Okay, so these prevent the strings from accidentally derailing and starting to spin around and just getting tangled up. They ensure that the string has to stay within those little pulleys. Otherwise, you're going to have a mess, just a rat's nest of tangled string. If they were to pop out from their tracks, they need to stay spinning right where they belong. So that's what this is for. And then I added this extension, this butt end of it, which is right here. I added this part so that these guidance hoses can also be strapped into place in the proper spots lined up with these holes. And I can just wrap this in electrical tape to pin these two guidance hoses to this little guidance hose strap down mechanism, a little L shape extending from the original thing. So first I just had these sculpted out and 3D printed, and then I was like, you know what, I should have something where I can secure the hose, the guidance hose, exactly where I want it. So now the string will wrap around here, being pulled through these guidance hoses as it wraps. Also, as a side note, one string will wrap clockwise and the other counterclockwise. And so what that will mean is as the motor spins clockwise, one string is being released and the other is being unraveled, which is exactly what you want, since one motor is to control both forward and backward movement of a given joint. So one string, which is being drawn in as the motor turns, is acting as flexion, and then the other string, which is being released, is acting as extension. So we got flexion and extension. The topmost one I'm always going to have be for extension, and the bottommost one I'm always going to be flexion. And that's just a choice. I could flip-flop that, but I'm choosing that because it's more intuitive for me. Okay, so that's how the idea works, and that's how it's all being kept nicely grouped together. Now, back to the original problem which I was presenting to you guys, which I uncovered, which is this. These motors rotate at 3,000 to 6,000 revolutions per minute. They rotate really, really, really fast. And the problem with that is they're then designed for speed, but not torque. You can have either speed or torque. You can trade speed to get back torque, or you can take away torque to get back speed. They're inversely proportional. So this motor is really, really, really fast, but extremely weak. If you were to grab the output shaft, you can stop it easily just with your finger. So that's a huge problem with these motors, which is why the standard hobbyist servo here you see all the gear train, right? Look at how it works. It's so cool. This thing's spinning a million times just to get this to spin once. Look how slow that's spinning, and then look how fast that's spinning. It's slowed down by a lot. Now you might be asking, well, how much slowed down is it? How much geared down is it? Well, I did a little research, and I found out for every 180 turns of the motor's output shaft, this output, the final output, turns one turn. So it's a 180 to 1 gear reduction. That's insane. 180 turns equals 1 turn on the final output. So, because I have no gearing system, I stripped that out for space-saving concerns. I'm stuck in a situation where I'm going to have an extremely fast motor that will bend a finger joint just so fast, faster than I can see, but so weak that the hands wouldn't even be able to pick up anything. They would just be completely... I mean, I'd be lucky if the fingers moved at all, even carrying its own weight. Just to be able to lift a finger to move would possibly be compromised. That's how weak we're talking about. But it will try to do it really quickly. So what we want to do is trade down that speed in exchange for torque. How do you do that? By gearing. But we've already found gears take up too much space. Plus, if I wanted to create a custom gearing system, so like let's say the motor's faced like this, instead of the gears coming out like this in an L shape, what if we could put the gears side mounted to the motor in order to slim down the profile? Well, that would be something definitely worth looking into if it weren't for one problem. How then am I going to create gears that can then come off the geared output shaft of the motor and then turn? That's another type of gear that can make a turn. They can do that. And then tap into the gear train, which is flush, running parallel to the motor instead of perpendicular, how they got it. That would require custom gearing, which is extremely difficult to make. You would have to have very excellent milling machinery that's able to do fine precision milling work. We're talking about, I mean, for that level of detail, that's got to be, you know, $30,000 machinery or whatever. Just extreme precision stuff. Probably more than that. It could be like $200,000. So that's just out of the question. Plus, we're trying to keep this attainable on a DIY budget, and we're trying to keep it practical. So that's out. It's not an option in my opinion. Pulleys then are the answer. So I showed you guys in a past video my tentative pulley system, and it was pretty cool. And then I did another video update about pulley blocks. I was actually watching Gold Rush, and there was this episode where Tony Beats and his son were trying to pull a barge out of some water with a tractor winch or whatever, and the winch wasn't strong enough. So they wanted to double the strength, and they used what's called a snatch block, which is just a type of pulley. And that was able to double their strength. So I was learning about that. I was like, that is amazing. That would be so easy to make. So I'm going to make that. And so that was my new plan. Instead of having like actual pulleys that spin that are lined up next to each other, and one big pulley and then one little pulley would then be like a gearing system, I decided, you know what, I'll just use snatch blocks. That's even better. So as I was looking into building my snatch block pulley system, I ran across the most incredible thing, which is this video here called Why Snatch Blocks Are Awesome, How Pulleys Work, Smarter Every Day, episode 228. And this system is perfect. But let me get back to the math. Well, first I'll show you guys this system, and then I'll get back to the math. Okay. So they were showing first, let's see. They go through a progression. So first they show you just like the basic, where it's like, okay, this pulley is just for redirection, so that when they're pulling down, it pulls up. So that's just a redirection pulley. And then this bottom pulley is the key. This is the one that makes the mount. They have to cut in half as far as the required force required to lift this cinder block. It's cut in half by this pulley. Now, what that means is they have to pull twice as far to lift this thing half as much. Or with half as much force required. So they're trading speed for force. They'll have less speed because they're having to move this string twice as far. So their speed of movement here at this pulley is going to be lesser. But the torque is increasing, so to speak. The torque at this point. So this point would be similar to the point where my motor is reeling right here, where my little pulleyed output shaft would be. Now,
pulley, because that's what pulleys do. They redirect force. But down here with the snatch block, we're doing the same thing. We're redirecting the force. But you have tension in the rope and tension in the rope. So all you do is you put tension in a rope somewhere, and then you add up as many ropes as possible on the thing of the rope. And remember,
here he's showing that you can. This first one does nothing, but then this one right here, this cuts your speed in half but doubles your force. And then this one also cuts your speed in half but doubles the force. So this would be 1/4 strength or whatever. So that's a little more sophisticated. Now remember, we're trying to cut down 180 to 1 if we're to match a hobbyist servo. But we don't actually have to do the full 180 to 1. because we're okay with having it be 6 times faster than a standard servo. So we only need 180 divided by 6, which is 30. So we're looking for a 30 to 1 down gearing of the speed of our motor to exchange speed for torque. 30 to 1. And so then he shows this, which does a lot more. And I think this was an 8 to 1. And then, so this would be hard now to manufacture because you're looking at a lot of like fine parts, right? You've got like 1, 2, 3, 4 spinning wheels that spin freely with grooves on them, and you've got your container system. This would be at the scale I need for these little tiny servo motors, and we need to have these once for the flexion and once for the extension on each motor. We have to create our own separate pulley block system. So we need 2 setups like this per motor. So we would need 1, 2, 3, 4 total these things per motor. And we're going to have, I think it's 32 motors just in the arm. So 32 motors times 4 of these, that'd be 120 of these little mechanisms at a tiny, tiny scale. My 3D printer can't do it. So I was running into another problem, like, oh no, I cannot make this. This is just going to be way too hard. And then I even looked up, like, miniature pulleys. Maybe I could buy it. And look at how the smallest ones are, like, extremely bigger than I need. Let's see, I think I just did an image search. Yeah, this is, like, the smallest of the small. And here's a penny next to it. I would want it to be like 1/30th that size. I mean, we're talking tiny. Tiny, tiny. Okay. So I'm like, man, now what do I do? Like, I can't even make this at a small scale. So then he shows this. It's kind of just the one we just looked at, but broken out. And I'm like, maybe I could do something with this, because these are more simple. I could probably do something. And then he does this big reveal, and he's like, guys, you can make all this way easier the way Archimedes did it with this. This was the big reveal, which was the eureka moment, which blew my mind. It's when he showed me this. This is crazy. Let me show you guys what he revealed right here.
Smash blocks are awesome. There's a type of pulley system we haven't talked about.
Oh wait, I gotta put it at normal speed because you guys won't understand at 2x speed. Okay, here's at normal speed.
Yeah, it's a compound pulley system. You remember the block and tackle? We had an 8 to 1 mechanical advantage. Well, this has the same mechanical advantage, but it does it a different way. You remember we add up the tension on these ropes, and we have 1 plus 1 is equal to 2. But if we have 2 plus 2 is equal to 4, and 4 plus 4 is equal to 8, we can come up with an 8 to 1 mechanical advantage just like that with less pulleys. This is fascinating, and one of the first people to come up
was Archimedes. Okay, so look at that motion. I just had to watch this over and over and over while thinking. This blew my mind. I just played this over and over and over.
The same mechanical advantage, but it does it a different way. You remember we add up the same mechanical advantage, but it does it a different way. You remember we add up the tension on these.
Look at how this one moved a ton, and then this one barely moved, and then the one below it was like still. Practically still, comparatively speaking. And I was like, wow, so each one, the speed gets slower, but the torque gets higher. Remember, we want to trade speed for torque. So this one's zooming up, this one goes flying, then this one's like all sluggish. The one below it's even slower. And they're all aligned in such a vertical, and look at the flat profile. Look at how flat that is. And so I'm like, that will definitely fit anywhere I want it on the robot, because it's got such a flat profile. It doesn't matter how wide it is or how tall it is. If it's that flat, it can be flush against anything. You can squeeze that into any nook and cranny of the robot. It will fit, especially on the tiny, tiny scale we're going to be using. So this is so much better than a gear train. Now remember, he said this one's 2x force, but 1/2 speed. And then this one does that again. So then he said 1 plus 1 is 2, 2 plus 2 is 4. So this one's 4x torque, 1/4 speed. So you're knocking down the speed overall to 25% of the original output speed. And then this one is 8x torque, 1/8 x speed, or 1/8 speed. So now we're at 1/8 the original speed of the motor. Now if we added another one, just visualize 1, 2, 3, adding more and more, we could go 1/16 speed, 16x force, and then you add one more diagonally from there. If you visualize it being down here, and that one would be 1/32nd speed, 32x torque / force. 32 times the force of the original motor. Now we're getting to where I said I'm willing to make mine 6 times faster than a standard servo motor, but it'd be 1/6 as strong. That's your trade-off. And I think that's acceptable because I don't need it to be that strong. Plus, if you picture that original standard servo motor, look at where normally you're connecting to. If you look right here, normally you would connect the tip of this output shaft to your thing being actuated. The tip of it. The further away you are from this fulcrum, the less torque it's going to actually have and the more speed. So they just got done down gearing down to a really slow output, and then because they use a huge servo horn, they're now going back to speed and less torque. So they're undown gearing it by using a giant servo horn. So they're like undoing everything these gears did. Not everything, but somewhat. So I think they said like at 1 centimeter away, you already lose like half the strength and you increase the speed by double. And then like 2 centimeters away, you're like at 4x the speed and 1/4 the torque. And then way out here, you're like at 1/6 the speed and 1/6 the torque and 6x the speed once you're kind of out here. So by me having my string wrap right around here anyways, because my string wraps nice and snug to here, it never gets way out here, we're making up for some of that lost torque anyways by keeping our string real snug. So basically, that is where I get that 1/6 number. And I go through the math a little bit more as well. Okay, so my motor on 16 turns, it draws in a full 5 inches of string onto the pulley wrap. But we want it just to move about 0.3 inches at the end of the day, because that's all that's really needed for the finger joint to have its full flexion or extension. We just need a tiny amount of string to actually be moving at the end of the day. So 5 inches of string drawing is actually going to only move the final output of my gearing system to about 0.3 inches. And so basically, after looking at the math, about a 32-to-1 down gearing is ideal, and it's going to be comparable speed to a servo with the 180-to-1. Comparable, because we're hugging so tight to the shaft. That would be a little bit slower anyways on a standard servo. And even if it is a little faster than a standard servo, generally speaking, standard servos do come across kind of too slow for most robots anyways. And so we're looking to use a lot of motors to compensate to get more strength and while maintaining speed. So it's like if you want speed and strength, you got to use a beefier motor, right? So you can either use a giant beefy motor or many small, somewhat beefy motors that collectively add up just to give you a lot more horsepower. And you can see all these motors I've got designed to fit. This is all to scale, by the way. All these motors just in the forearm, tons and tons of motors. And then the inner forearm, I've got tons of beef right in here and tons of motors here. There's a ton. And look at all the motors I got in the thighs. I mean, it's Motor City. I can empty out a hobby shop all their motors that are going to fit in my robot's thighs. Look at all them. And we got some real big motors. I think, let's see. Yeah, right here is a jumbo motor. This is probably for like the calf or the quadriceps. I'm not sure. We got some real beefy motors mixed in. These two, I think, are the skateboard motors for electric scooters, skateboards, or whatever. So, I mean, this is going to give a ton of power. But for like lower back, we're using like a ton of motors that collectively add up. And then we got some motors snuck in here too. And we got a few motors that we put in around here. But to keep a flat profile for the chest, we couldn't actually fit any motors because it actually gets really flat. And the arm needs to be able to go like this, like come all the way across the chest to have full flexibility range of motion. So any motors would prevent the full range of motion of the arms. So that's why we couldn't put too many on the inner arms up here or on the chest. So anyways, yeah, we're going to have a ton of motors. I don't even know. That's going to be such an insanely complex job to even do. But, so yeah, I was going to use then this type of, what do you call it? A compact pulley system. And 1, 2, 3. I was thinking 4. We can go up to 5 of these little pulleys. Now I was thinking, but how do you create these pulleys at a small scale? And here's where real creative thinking had to really save the day. So I was thinking, like, do I actually need a rotating wheel? Or can the string just wrap around something and just slide without an actual wheel? And so, guys, it just hit me how to do this, and it blew my mind. And I'll show you guys how I can make a pulley like that so tiny. I mean tiny. Okay, so this is going to blow your minds. Prepare to have your minds blown. This would be the type of thing I'd keep a secret if I were having this closed source. This would be like my secret sauce, the reason why I'm successful, that type of thing, which other people could not replicate, you know, which makes everyone scratch their head like, how did he pull this off? This would be one of those moments. This is like proprietary type stuff. Like, you wouldn't want to tell people this, because this is what's going to enable me to be able to pull this off, fitting so many motors like my diagram design you just saw. Okay, like, how can he fit that many motors? Wow, what the heck? So to create those little pulleys, oh my, I mean, I'm having a hard time even holding onto this. Let me get my precision tools. I can't even do this by hand. I mean, maybe I can with a couple tries, but let me just get a little bit of help. I mean, this is tiny scale, guys. I don't even think you guys can see what I'm doing yet. That's how tiny this all is. Okay, got it. Okay. Okay. You see the string? Okay, it's going through what's called a PTFE, or Teflon tubing. Okay. And it looks kind of like a shovel handle or a stirrup. We could call it a stirrup, like stirrups that are on the saddles of horses. And so basically, this will act as our pulley. Obviously, the stirrup's gonna like get all messed up because I'm holding it funny or whatever, but you can see the concept here that this string will pulley through. Okay, but the plastic PTFE, it rotated up the stirrup, so we would actually sew it in on both sides so it would lay flat. This just turned vertical. It tends to do that, so we would sew it tight on the left and right sides so it wouldn't do that. It keeps wanting to jump out of the way. But the idea here, let me go back to maybe drawing so I can illustrate how it's supposed to look. Okay. So you would tie the string off here and then tie it off here, sewing into the fabric we have taped and sewn down onto the bones. We call it our bone fabric. And then our Teflon tube would run from here to here, right? And then our string, our muscle string, would come around, wrap around, and then come down. And that would act then as a pulley. And then we could put let's see. Yeah. We could tie off some string here, run it across, and then tie it off here. As snug as we can to here. I drew it kind of far away. So more like from here to here. Okay. And what that will do is it will keep the main string coming through this inside the channel so it doesn't pop off the pulley and end up like rubbing rope on rope. And so the idea here is the PTFE tube could theoretically rotate a little bit, but I don't think it will be able to. I think it's actually going to stay stationary. But this string, which acts as the muscle, will be rubbing on a very slick plastic surface that's rounded. And we can actually put grease on the string and on the plastic surface, which will be slippery. So though it is a friction pulley, we'll call it, it's at a microscopic scale because this is 0.3 inch diameter, or no, it's 0.3 millimeter internal diameter, 0.3 millimeters. And then the total length of this, I have like maybe 2 to 3 millimeters. So I mean, this is a tiny, tiny pulley. Like this whole setup is like 3 millimeters. Quick editor's note. You should probably put a little bit of glue on each end of the Teflon tube pulley, as a standoff to lift it up a little bit off the surface that it's attached to, so that the pulley rope that's sliding through it is not rubbing on the surface the pulley is attached to. It needs to be slightly lifted off of that to minimize friction, so that the only thing the rope is rubbing on is the Teflon pulley stirrup or ladder rung itself. That's the only thing we want rubbing. 3 millimeters. So this is as tiny as it gets and basically free because it's just a little bit of string and a little bit of PTFE tubing, which we already bought for the muscle guidance hose to actually guide these strings to make turns and whatever, and provide slack where it's needed and whatever. As opposed to like a fishing line where you just have the string go through little hoops. We're doing it more like bike brakes where the string goes through actual guidance hose. And you'll note that with bike brakes, the hoses coming off the handlebars are very slack, which allows for you to turn the steering of the bike handle. You turn that, and that would actually activate your brakes if it weren't for the fact that the hose adds length to the wire that runs from the squeeze handle brake handles to the actual wheel brakes. The hose provides the required slack so that even while turning, you can deploy the brakes, and the turning doesn't actually affect the braking. And actually, I learned that the hard way. One time I was fixing a bike, and I took that tubing off, and I just ran the wire straight to the wheel, and every time I turned the bike handle, the brakes turned on. I was like, what the heck? I almost flew off the bike. And then it hit me, oh, that's why the hosing is there for the wire. It gives the wire the extra length it needs so that when you go to turn the bike, the brakes don't deploy. And so that's the point of the wire. And so that guidance hose, that's the point of the guidance hose. And so that guidance hose is then needed in order for, if the robot's finger were to be moving while the wrist is deployed, the movement needs to not be affected by the wrist deployment. So you would have extra hose near the wrist that pulls a little more taut when the wrist bends, but that hose is a little loose here. If the wire were just connected from the motor directly to the finger, when this does this, this would pull in because the wire would get pulled taut by the movement of the wrist, because now it needs to travel a further distance from that motor to the finger. And so that's what the guidance hose tubing is. And finding tubing for that, I didn't think I could do it. Like, how do you find tiny, tiny tubing? Well, I just was fortunate. I stumbled across it. It's called PTFE Teflon tubing. You can buy it in different sizes. I bought the 0.3 internal diameter by, I think, 0.6 outer diameter PTFE tubing. It was perfect for the upholstery thread I'm using as the muscle thread. But we're going to be using like 200-pound test Spectra / Dyneema thread, fishing thread. No, it's a 100-pound test. It's 0.55 millimeter line. So we would need for that like a 0.6 millimeter internal diameter Teflon hosing, which they have all different sizes, so I can definitely find that. And that will be the guidance hose for that thread. For the beefier motors, like the skateboard motor, it will use that. Quick editor's note, we actually will not be using the skateboard motors after all, because they are outrunner style, and the way I'm doing the cooling system for the motor's cases prevents using an outrunner motor, because the case itself spins on an outrunner. That's going to mess up my whole design. Plus we want to be able to sew things onto the motor, like mount circuitry to it or whatever. So the idea of having a spinning motor case is horrible. I want just the shaft to be spinning. So we're not actually going to be using those particular motors that are for skateboards on this project. And I actually did go ahead and buy a replacement motor for that, which is called a 4082 brushless DC motor. It's comparable strength, I believe. It's also 930 kV, 3400 watts. It runs from 36 to 52 volts and at 64 amps. It's in-runner style. It's 1/7 RC motor. And so that should be very similar in specs to the N5065 brushless DC motor, which runs from 11 to 36 volts, 2500 watts, 80 amps, 330 kV, outrunner style electric skateboard scooter motor. That one was $29 a piece for the electric skateboard scooter outrunner motor, which is what attracted me to it a lot. Whereas this in-runner motor, that's slightly smaller and slightly narrower, you can see the form factor difference here. Here's the skateboard outrunner one, and here is the one I'm replacing it with. They're about the same size, but this one's just fatter, this one's longer. This one costs $65, this one costs $30, so I didn't want to spend the extra money, but I have to because I need in-runner, and I need around that size, and that's all I can find that's in-runner. And I'm happy with that size, but I did have to rearrange my blueprint slightly to accommodate the slightly different form factor motor, but that was not a big issue, and I got them all to fit again. In fact, it might even need something more strong than that. It might even need 2 or 3 of those woven together, or no, it'd probably use a couple of those woven together, maybe. I don't know. So anyways, I showed you guys then my solution for creating these tiny, tiny pulleys, and I would like to show you now a drawing or a series of drawings I made for how these pulleys are going to actually look on the robot. Okay. So I just went through a progression of just trying to understand how all the pulleys work. And so I'll just go through the progression. So here we have just a motor with no pulleys. Here's the little motor, and here's the 2 strings running through guidance tubing to where the finger would be. And then I'm like, okay, a little more advanced. Here's the little motor. Let's just draw 1 string at a time. Here's the string. It goes through, and then to a finger and ties off. Or no, it would tie off into just nothing. That wouldn't be moving. That's just stationary. This string goes then off to the finger, because this whole little shovel handle looking thing is going to get pulled upward as these pull tight. And so this would be 1, 2, 3, 4, 5x. I think, yeah, 5x force increase and 1/5 speed, I believe. No, it's probably going to be 4x. Yeah, it's 1, 2, 3, 4. I don't think you count that one. So 4x force increase. And then this one would be 1, 2, 3, 4. Wait, 1, 2, 3, 4, 5, 6, 7, 8x force increase. And remember, we're going for 32x is what we want, so we would have to do a couple more turns like that. And so I thought this would be fine, but it's really not ideal. This was the design I was thinking of using until I saw that video, the compound pulley system, which was way better than this. And then here's the compound pulley system, and here's the full 32x. So we got the motor here, and it goes up around a pulley, ties off. A little string comes off the top of this pulley, comes around this pulley, ties off. A little string comes off the top of this pulley, around this pulley, ties off. A little string comes off the top of this pulley, around this pulley, ties off. A little string comes off the top of this pulley, around this pulley, and then goes all the way to the finger. And that is 1, 2, 3, 4, 5 total pulleys. And that would be a 32x speed reduction, or 1/32 speed and 32x force increase. So this super fast spinning motor now is 32 times slower, but 32 times stronger. And you can add as many pulleys as you need to increase the torque coming out of this while decreasing its speed inversely proportionally. And so what I realized is all these tiny, I showed you guys, each one of these is only 3 millimeters wide by 3 millimeters tall, the total setup in this drawing. And so this is tiny, tiny, tiny. As tiny as you can cut it, and as tiny as you can get this string around and sew it in. I mean, this can be done just miniature. And that's how we're going to make these pulleys here. And then here, I'm not actually sure what I drew there. Here's something else. Oh, I was kind of elaborating on that type of design with this. So yeah, the motor string would come in, it would wrap several times, and then tie off there, and then as this pulls, this thing would eventually, this whole bottom triangle would get reeled upward as this pulls taut. All these would tighten up. Kind of like when you, oh, you know what, this is kind of like tightening your shoe. You guys know, like, if you have a loose shoe with all the shoestrings, if you pull hard on this, the two sides of your shoe draw together. It's the same principle. So yeah, this is just like when you tighten your shoes with your shoestrings before you tie the shoe knot. It's the same exact principle. And so you're actually able to create a lot more force when you pull on your shoestrings to draw together the two sides of your shoe. Same thing. And so one side of the shoe then would be attached to your finger, and the other side would be attached to the motor, and this would down gear the motor. But like I said, I I felt that this would be inferior to this because this complex pulley system actually is twice as much. You need half as many pulleys as you do with this. So this is like the dumbed down version of this. This increases force exponentially because it's like it was one plus one. Okay, this is 2x. 2 plus 2. This one's 4x. 4 plus 4. This one's 8x. 8 plus 8. This one's 16x. And then this one's just a redirect, I think. So this one is actually 16x. We would need one more pulley here. And then it would need to come off here and go down in order to make 32. So we need one more pulley for 32. So this is actually a 16x system, not a 32x. So we just need one more pulley and we have our 32x. But I think the 16x I actually wanted to try first to see if it was actually strong enough, because I'm okay with it not being that strong and just being really fast at this point. I want fast moving fingers because, like, you know, that'd be cool if the robot could really move fast and like like typing fast and moving fast. But then, you know, you also want some degree of strength. So you got to play with it. I mean, at this point, like, for sure, I'm going to need trial and error. I did a lot of math. You guys saw some of it and some of my thinking with the math. But you definitely need to have also some degree of experimentation, too. The math and the visualization and using your gut instincts and common sense, that saves you a lot of experimentation. Because you can visualize, oh, that's not going to work. Oh, that I think that might work. So visualizing and stuff saves you from having to go through a lot more experimentation, which then saves time overall. But at the end of the day, you only have so much time to do experimentation, so you want to try to avoid it, as much of it as you can, by really thinking about it a lot. And that's part of why I think my robot project's taken me so long, is I'm trying to make something that's really, truly state-of-the-art, next level, and on a budget. Something that other people can follow after my footsteps and achieve similar success. And so I think it's really good and important that, you know, I'm revolutionizing the field. I'm not just slapping something together. I see too much people just slap something together and they end up with a robot that's just like, hello. It's like Sophia robot and stuff. They just move just terrible. I want mine to be like, hey, what's up? You know, shooting baskets, like just smooth looking human completely. And being as strong as human and possibly even a little faster than a human with precision that's far exceeding human capabilities. I mean, I'm looking for something that is mind-blowing. I'm not interested in a project of mediocrity. I have no interest in that. I'd rather not build a robot at all than build a mediocre robot that is embarrassing at the end of the day. So I'm going for greatness with my robot. And I don't mean I want to be great, pride, this and that. I'm not saying that. I'm saying that the robot itself, the end result is a great end result. And we should do all things to the very best of our ability as unto the Lord. So that's what I want to do. I want to do an absolutely fantastic job. Alright, the other thing I wanted to point out, okay, so this is the first motor we're doing. This motor goes to the distal of the index, so it's actually this movement right here. Yeah, most people do one motor that does the entire movement of the finger. I disagree with that. I think I want to have one motor do this, one motor do this, and then one motor will do this. So I'm actually using 3 motors, one for each joint, but then this, since it goes left to right and front to back, needs 2 motors for it. So that's 2 plus 1 plus 1, 4 motors per finger for each of the 4 fingers. And the thumb is going to have 1 motor, 2 motors, 3 motors. So 3 motors for the thumb, and then 4 for each, no, 3 for each finger. No, 4 for each finger. 4 for each finger. 1, 2, 3. 3 for the thumb. So that's 4, 8, 12, 16, 17, 18, 19 motors just for the fingers and thumb. And then we got 1 motor will do this, 1 will do this. So that's 20, 21. And then we got this one's a motor, so that's 1 motor, so that's 22. And then we got bicep, tricep, 23. So something like 23 motors. But anyways, this is for, like I said, the distal joint of the index. And its guidance hose is going to come off of here. And you guys saw how that looks with right here. You can see the guidance hose comes up and then comes along the arm. So that's going to come up. Hold on. That's going to come up to the back of the arm where I have no motors planned. It's all free space. So it's going to wrap up to here. The hose will end right about here. And then it's going to come out, and the little pulley system, 32 pulleys, will be between my thumb and index finger right here. It's just going to be a bunch of little moving pulleys up and down right here. And actually we can get like I don't know what was it, like 5 or 6 total pulleys. But you guys saw how tiny it is. So that'll be a pulley. Like they'll all be real closely spaced together. And from the output of the tube to the first pulley, since the motor takes up in 16 turns, it takes up about 5 to 5.5 inches, let's just say 5 inches of string it's going to reel in. Then 2.5 inches, which is about this, from my thumb to my index finger, 2.5 inches from the tube to the top of a pulley and then back down will mark the total travel distance of that first pulley. And if you guys recall, the first pulley is the one that does the big moving. Remember when he pulled on this, that first pulley moves from here all the way to the top, and that's the full range of motion you can get. So the distance from here to here has to be 2.5 inches, and then from here to here 2.5 inches, for a total of 5 inches drawn in. Yeah, so, and then the distance from here to here can be real close. You want them as close as possible to keep all these real compact. And we'll have a nice flat profile with the way we're doing it. Now, technically, whenever you have a pulley, you want to have a you want to have a bearing, which has little metal balls running around the track, and then they're heavily packed with grease, and it just spins so easily, like rollerblade wheels. And you want to have that inside, in between 2 plates, and then you want to have the bearing have a little grooved wheel attached around it, which the string will slide through. That's ideal, but that's for large scale. If you're doing something less than 3 millimeters in total diameter as your pulley, nobody makes pulleys that small. They can't even do it. It's almost impossible. I mean, maybe somebody can do it. So basically, in that case, we are stuck with a non-traditional pulley system, which means we're relying on friction. It's like if you took a rope and I held one end and you took it and walked, a few feet away, you wrapped it around a PVC pipe, and then you brought it all the way back, wrapped it around another PVC pipe, and then wrapped it back and then tied it off, and then you tied the second PVC pipe off to a weight in the corner, and now I'm to pull. That would be a comparable system. And the problem with that system is my rope now is rubbing on PVC pipe. Now, because a rope is pretty slick, it's made of nylon, and then the PVC pipe is pretty slick and rounded and smooth, the friction should be minimal compared with if you did that wrapping ropes around trees. Now you got that tree bark, and my rope, let's say the rope was made of like burlap bag type, rugged, rough rope, then there would be so much friction that it would be like just kind of ruining it and producing a lot of heat. But since I'm dealing with nylon upholstery thread and Teflon tubing as my stirrup pulley, which I showed you guys earlier, the friction should be very minimal. And if you add in lubricant slapped all over the string, I think the friction is going to go down to almost zero, because you're dealing with string wrapping around that tubing, the tubing slick, the string slick, and now you're lubricating it all. And then it's not rubbing for a very long time. It just rubs over a little bit as it's passing through. Now, I did consider this, and I'd like some opinions on this. If I were to use a larger diameter, let's say 0.6 millimeter or 1 millimeter diameter Teflon tubing to wrap my string around that, would my string have less friction the bigger the pipe? Like, let's say the pipe were this big and my string's wrapping around that. Would that have less friction or more friction than wrapping it around a tiny, tiny pipe that's only 1 inch in diameter? I feel like making such a sharp turn could actually be bad for friction, because you're like concentrating all the directional changes to a tiny area. If you look at pulleys, usually the string wrapping around pulleys takes like a kind of a wide turn. It doesn't like go around a tiny little pulley and then come straight back. So I feel like the wider turn of the string is beneficial. But then, since my pulley is a friction style pulley, it's not going to operate by the same principles as a bearing style pulley. Maybe they're just doing that because they need a pulley with adequate strength, and so they just need to make a bigger pulley, and they need bigger bearing balls and everything else. And so it's not so much the sharp directional change, it's that they're just trying to build a stronger pulley, which is then naturally bigger pulley. So I don't really have much to go off of, since most people don't use pulleys that actually are rubbing. They use pulleys that are actually a bearing system. So I don't really have anything to compare or research on that. So I feel like there's a trade-off, because like the bigger pipe, if you're rubbing along the whole time, that's more contact area for friction to be developed. But then it's also a smoother transition, because you're going that way and then you change directions. It's a smoother change of direction. It seems like if you just made it like 0.001 millimeters and the string has to go and then turn, that would like kink the string. Like it needs to have some curvature before it starts coming back the other direction, presumably. So it may be, and maybe I'll need to test this actually, but it may be that maybe like a 1.5 millimeter diameter Teflon tube is my stirrup style pulley. We're going to call it a stirrup pulley because it looks kind of like a stirrup. Might be actually superior to a 0.6 millimeter outer diameter Teflon tubing stirrup pulley. That's a mouthful. So basically, I think it might be a smart idea to try both and see which one does better. But my gut tells me it's going to be pretty similar, especially since we're greasing it all. Since we're greasing it, like, I just feel that the friction is just going to be negligible. So I'm just going to go ahead and go with the 0.6 millimeter outer diameter for now, and I may at some future point try out the slightly bigger stuff. The bad thing is, like, whatever I go with, I'm kind of locked in-ish, because then, like, if I had to redo it to the bigger diameter Teflon tubing in the future, I would be redoing a lot of these. Because, look at this. We're doing, what was it, like, let's say like 5 or 6 of these Teflon tubing pulleys per motor, but that's just per one direction of the motor. Remember, there's 2 strings coming out the motor. One's for flexion, one's for extension. The opposing muscles, so to speak. So, that'd be 5 pulleys per string for 2 strings. That's 10 total pulleys per motor. And I already showed you guys there's like 19 motors just for the hand. So that's 190 at 10 pulleys per motor, 19 motors, 190 of these pulleys just for the hand. Which shouldn't be that shocking because technically if you were to look at a standard hobbyist servo motor, it's got what, like 10 gears in it? And you're going to be using just as many of those for a hand, unless if you cheat and use one motor as the whole finger, which I'm just so against that. Like, I feel like the finger, I don't know, like, though one motor technically can do this, because it seems like it, I mean, no, I don't know, maybe we don't have independent control. I think it actually is one ligament for the whole finger. Although this proves that I think there might be a separate ligament for this bottom joint because you can keep it straight for that. But for these two, for sure, for this one and this one, I think that could be one motor easily because they do seem to move proportionally to one another every time. But here's why I don't want to do that. First of all, that would only save me 1, 2, 3, 4 motors would be able to delete. And then one motor would do these 2 joints for each finger. So we would just be saving 4 total motors out of 19. That's not that big of a saving. It would drop us down to 15 motors for the hand instead of 19. Big deal. Like, if you can fit them, why get rid of them? And check this out. If you got rid of those 4 motors, you're cutting the strength of the fingers in half because we could have had an extra motor really tugging down on that fingertip joint. And when you think about what am I doing when I like grab tight to undo this peanut butter, like I'm gonna, or like what about like rock climbing? Like you need to really bear down on those fingertips, like really tight to be able to pull your whole body weight. So to take out the fingertip motor seems like a stupid decision long term. I would be kicking myself when the grip is, it's strong, but it could just be a little bit stronger. I'd always be wondering, man, if only I had kept my design with those 4 motors in, I wonder how much stronger its grip would be. I wonder if it would have been able to actually climb a tree or do rock climbing had I just added those 4 more motors. So I'm not going to get rid of those 4 motors just for making the design ever so slightly more simple and space efficient at the expense of performance. Performance is king, guys. We want to have speed and strength. With motors you get less speed for more strength, or you can get more speed for less strength depending on how you gear them. And I want the best of both worlds. I want a robot that's fast and a robot that's very strong as well for every joint. And so we want to oversize the motors and have a lot of them. As much as we can. Now, I used size 140 brushed DC motors as my design for the fingers because they're very inexpensive. I think it's like $5 per motor or less. I forget the price now, but it's very, very reasonable. And actually I could look it up real quick. Let's see. Brushed DC motor size 140, 86 cents. Wow, I didn't realize it was that cheap. It's 86 cents per motor. That's mind-blowing. How is that even possible? Maybe it's more now with inflation. I'm not sure. That was literally like 2 years ago when I bought them, before the pandemic. So 86 cents per motor. Yeah, I'm going to want to use some of those. So approximately like maybe 15 of those I think I use per hand. I may use some of them for facial expressions, but pretty much they're not strong enough for my preferences, even though that's probably what's in every hobby servo that you guys buy. It's these little 86 cents motors. I'm going to be able to produce greater strength in the hobbyist servo when I bump up to the brushless DC motor size 2430 for $11. Now we're talking about 5800 kV, 24 amps, 7.4 volts, 200 watt motors, and they're not that much bigger at all than I mean they're a fraction bigger than the 86 cent motor, but they're probably like 3 times as strong. So that's what I want to go for most of the time. It's only $11 per. So I'd bump up to that size for any, even I think maybe even for the thumb. And definitely it's that size and greater for most of the robot, most significant, strength requiring motors. But like facial expressions, you're not too worried about strength. And it's like fingers, it's like you are worried about strength, but like I don't know. To be honest with you guys, I do wonder if I'm going to regret using the 86 cent motors for even the fingers, because I could have had grip strength maybe 2 to 3 times stronger if I would have went with the brushless motors, the brushless size 2430 motors for $11 each. It's possible that I'll regret that decision, but it wasn't just a cost savings thing, it was also a size, a space savings, because look at this. So here's the size, what did I just say? 2430 for $11. It is right here. And these are all to scale, by the way. And here's the 86 cent one. So you can see it's like 40% bigger or 70% bigger. It's significantly bigger. And you can see all the 86 cent ones I'm able to store in this forearm right here. I would not be able to store that many of these because these are significantly longer and beefier. So I just could not fit them all in the forearm. Not this many for each individual motion of all these different little fingers. So that's why I went with the smaller ones for the fingers. If I had more room in the forearm to where I could fit all 22 being this size, I'd do that. But I don't have that luxury because I'm dealing with a pretty tiny thing. Also note that I can't put any motors in this channel because of the pronation of this bone. As the hand rotates, this thumb's going to come down this way, and then these motors swing around and almost touch these motors. So you can't fill this gap with too much stuff. So that's why I have it all emptied out here, because this is going to rotate. These two bones rotate around each other like this. So yeah, so that's the real reason why